Okay. All right. It is my pleasure to introduce Golo Wimmer. He got his PhD from the Department of Mathematics at Imperial College of London with a thesis on energy conserving compatible finite element methods for numerical weather prediction, a topic that I'm very interested in. And then he joined Los Alamos as a postdoc for a couple of years and then transitioned to a full-time research scientist position there. So I'm so glad that he was able to join us. Without further ado.
Yeah, thank you for having me here. Yeah, thank you everybody for coming. Yeah, first I should say this is work I've been doing together with Konstantin Lipnikov, Ben Southworth, and Jianzi Tang. Also at my group, Applied Mathematics and Plasma Physics in the theoretical division of Los Alamos. All right, so first I'll give you a little motivation as to why we're doing the kind of maths we're interested in. And I'll show you a little bit about magnetic confinement fusion and the magnetohydrodynamic equations. And then after that, I'll talk a bit about a PDE structure, partial differential equation structure, that we're interested in maintaining after discretizing the equations, and why we're interested in maintaining the structure. And in particular, in our case, you'll be using the compatible finite element method to maintain our structure. So I'll talk about that. And finally, I'll talk about a little small side topic, which is kind of fun and interesting with compatible finite elements, which is axisymmetry, which is of interest for us in magnetic confinement fusion. And I was going to talk a bit about solvers, but I think I might not have enough time, so I'll have to skip that. And then in the end, I'll give you a little summary. Okay, so what's magnetic confinement fusion and why are we interested in it? The idea is that we want to harvest fusion energy to produce electricity. And, you know, fusion is produced in the sun, but it takes some incredible force to create the conditions for fusion. And in the sun, that is the gravitational force that squeezes nuclei together strongly enough that they fuse. But on the Earth, we don't have this kind of force, so we need something else. And there's various different ways of doing that, proposed ways. And one of them is to heat up particles until they're hot enough, such that they move essentially fast enough that when they bump into each other, they fuse. The problem is, for this to work, you need to heat them to 100 million degrees, which is not something that you can keep in a container and will just melt any sort of wall. So you somehow need to keep the particles away, or the nuclei and electrons away from your reactor chamber. And one way of doing this is if a gas gets hot enough, electrons and nuclei split, so it becomes a plasma. And in particular, plasma is magnetized, so it will react to magnetic fields. So you can use magnetic field lines to trap your particles away from your reactor chamber. And this is one configuration of how this looks like in practice. You have these concentric magnetic field line tubes that essentially trap your plasma away from the wall, and you have a bit of a vacuum between the wall and the plasma. And that's how you prevent the chamber from melting. And if you do a vertical cross-section, that's essentially how it looks like. You have these concentric magnetic field line tubes. And one issue with plasmas is that it can go unstable in many different ways. There's all sorts of instabilities that we need to be able to control in order to have commercially viable fusion power plants. And the reason why we're interested in Los Alamos is because Los Alamos works for the Department of Energy, and the Department of Energy is interested in new sources of electricity. And you can better understand these types of instabilities using computer simulations, because research power plants, fusion power plants, are actually quite expensive to build. So it makes sense to instead build simulations. And we have, for instance, microscopic effects where particles, for instance, bunch up together and poke a little hole into your closed magnetic field surfaces and then crash into the wall, which you want to avoid. But you can also have macroscopic instabilities where your flux tube, your magnetic flux tubes start wobbling. And when they wobble too much, they'll start hitting the wall, and then the hot plasma will destroy the wall. It will also kind of jank the magnets. And yes?
Is that an instability in control of the magnetic field, or is that something the plasma causes?
That's a good question. Usually it's more of a action-reaction kind of thing where you notice some instability is about to occur and then you try and control it to get it back in line. The basic configuration is supposed to be a stable configuration. So in practice, you just kind of wait and see what happens. And if you notice something might be off, then you start and try and control it. Yeah, so it's more of a, you can say, an intrinsic plasma issue in a way. Yeah. That's a good question. And it turns out different reactor designs try to address this. There's reactor designs called stellarators that are intrinsically more stable, so you have to worry less about control.
Stable, but you don't have to go very far in the state space to go.
Exactly. Yeah. You can imagine these red field lines, magnetic field lines, a little bit like a towel, and you put the two ends of the towel together, and then you start twisting the towel. Eventually, it will start getting, it wants to be a little wobbly, right? But here it's not wobbly at all, so it's not a intrinsically stable configuration. And these larger instabilities, these macroscopic effects, you can simulate using the magnetohydrodynamic equations, partial differential equations. And in fact, you can use magnetohydrodynamics to model not just the plasma region, but the whole reactor, including the walls. The magnetic field still acts inside the walls. Okay, so how do these equations look like? There's many different types, depending on how complex the simulation you want to build. Here, we're going to consider so-called resistive magnetohydrodynamic equations, where you have an ion density, ion velocity, pressure, and magnetic field that you want to evolve in your simulation. And your equations will come with transport terms that move around your density, your velocity, your pressure, and your magnetic field. So these are first derivatives, if you like. And then there's forcing terms in the velocity equation. So you have a pressure gradient, and you will have what's called the Lorentz force term. So in other words, the magnetic field will induce a type of motion through the Lorentz force term. And then you have dissipative terms. You have resistivity, which will slowly fizzle out your magnetic field. You have a heat flux, which will spread heat across magnetic field lines. And then you have viscosity, as usual, for a fluid or a plasma or a gas. And the viscous and resistive effects will heat the plasma, so you also have heating terms. So these are the type of differential equations that we are interested in and that we want to discretize to simulate our instabilities, macro instabilities. The equations come with a lot of different types of structure that we may want to make sure is still preserved after discretization. If you naively apply some kind of simple finite difference, finite element discretization on these equations, then this kind of structure might be destroyed after discretization, and I'll talk a bit more about this. For instance, the magnetic field is always divergence-free. There's balanced energy transfers between magnetic, kinetic, and internal energy. Internal energy is just the heat that's stored in the plasma. And then there's another structure which I won't talk as much about, which is called helicity, which is a measure of entanglement of your magnetic field lines. And if your magnetic field lines change the topology, the degree of entanglement, then that will change your helicity. So it's a useful quantity because it tells you about the configuration of your magnetic field. Okay, so next we'll talk a bit more about the structure and why it's important and how to keep it after discretizing in space. So the divergence of the magnetic field, it turns out if your discretization produces a non-physical divergence of the magnetic field, this will produce small wiggles in your simulation, and eventually that will lead to an unstable kind of simulation. So you want to make sure for stability reasons that your discrete divergence field is 0. And the way that you can show that the magnetic field is always divergence-free is you take the magnetic field equation, rate of change in time of the magnetic field plus the curl of the electric field is 0. You take the divergence of this equation, and then it turns out it's a vector calculus identity. The divergence of the curl is always 0. And that's always true regardless of what your electric field looks like. And then you can swap the divergence with the time derivative tool, and then you will find that the rate of change in time of your divergence of the magnetic field is always 0. So if it's initially 0, it will stay 0 for all time. And the key here again is that the divergence of the curl is always 0. So whenever you have an equation that says the rate of change of time of something plus the curl of something is 0, then you know that this field will always be divergence-free. If it is initially. How about the energy? That one's a little more subtle. You can have two types of energy conservation, it turns out, or two kind of flavors rather. One is total energy conservation, which is something that's often considered, for instance, in flux conservative forms of the equations. But you can also have balanced transfers between sub-energies. So you can have kinetic energy, magnetic energy, internal energy, and you want to correctly shuffle around these different types of energies. And why is this useful? Well, first of all, it's a guidance to stable discretizations. If you have a space discretization that conserves energy, you know it can't blow up in the sense that it can't spuriously produce infinite energy accidentally. So that's useful. But more subtle but more useful is it turns out you can show that energy conserving discretizations have a better long-term accuracy. And for instance, the climate research community is really into this fact, and energy conserving discretizations are useful for climate simulations. But then also something that's interesting is small scale accuracy. It's actually better at capturing small features in your simulations. And I'll give you a little example. This is not from magnetohydrodynamics, but this is from some atmosphere simulations that I used to do. Imagine you have a vertical slice of the atmosphere, a 2D vertical slice, and you have a cold air bubble that sits in this slice. And because it's cold, it will fall down to the ground, and then it will move along the ground, and it will produce this kind of stream here that has these vortices as the cold air flows along the ground. And the top row is a high resolution simulation, and on the left you have a non-energy conserving scheme, and on the right you have an energy conserving scheme, well, right or left depending on which way you look at it. And they look pretty similar. At the high resolution there's a little difference. You have a bunch of turbulence, little vortices, and the main vortex has its own smaller kind of vortices. But if you go to a lower resolution, these secondary vortices, wiggles, disappear. They get diffused away. The discretization can no longer express them. But the energy conserving scheme, you still have these secondary vortices that appear inside the main vortex. In other words, because you correctly transfer your sub-energies, you transfer enough potential energy, in this case to kinetic energy, you still get these smaller features, even though you have a lower resolution. So that's something nice to have. It kind of gives you a guarantee, even if you maybe towards being unresolved, because your grid scale is too small, too coarse rather, you can still get the right kind of features. As that's a subtle thing, but I quite like it. Okay, so how do you show energy conservation in your equations? How do you derive that? It's a little more complicated than the zero divergence condition. You have to take your full energy, in this case, kinetic energy, internal energy, magnetic energy, and then you want to derive the rates of change of these sub-energies. And the way to do this is you have to use your evolution equations from your original magnetohydrodynamic equations. So for instance, the rate of change of magnetic energy turns out to be the inner product of the magnetic field times the rate of change of the magnetic field. The inner product is just dot product and then integrated. You can see that here if you take the time derivative of h, this thing here is going to turn into b dot dp/dt. And then the ds, you just plug in dp/dt from your magnetic field evolution equation. And you know that dp/dt is going to be the curl of something. So that's it here. And you can do the same thing for the internal energy, where you plug in the evolution equation for the pressure, and for the kinetic energy, where you plug in the evolution equations for the velocity and the density. And then you look at these terms and you try and match them up, and that will tell you how does your energy flow for different types. So for instance, the magnetic energy term turns out to be equal and opposite to the term that you get from the Lorentz force. So that tells you the Lorentz force and the magnetic field transport term will shuffle kinetic and magnetic energy back and forth. Physically speaking, that happens when you have a wave, a magnetic wave, that will transfer magnetic and kinetic energy. And you can do this with every single term, and that way you can start matching up terms and you will get balanced energy transfers up to boundary conditions and forcing. And then the idea is going to be, can we do this after we discretize in space? And if we can, then we will get an energy conserving scheme. Okay, we are going to use what's called the finite element method. So now we want to discretize our equations, and we can use finite difference, or we can do stencil and grid points, or we can do finite volume. That is, we can represent fluxes across cells, or we can do finite elements, which is essentially you take E now that your solution is a function that lives in the function space. You can discretize the function space. You can approximate it by the space of piecewise linear functions that are linear in each cell, for instance. And what's nice about the finite element method, well, there's several things. One is it allows for general grids. You can pretty easily build all sorts of different meshes. And technically, you can build general meshes in any kind of discretization method, but it's a little more straightforward for finite element. There's some nice theory, which we'll get to, which is also not necessarily strictly finite element, but it also exists in finite elements. And then most importantly, I think for myself, is there's all sorts of finite element partial differential equation discretization libraries online that you can use. And they allow for easy prototyping. They're out of the box, massively parallel. You don't have to ever touch any MPI stuff. And there's all sorts of capabilities. For instance, there's Firedrake. It's a Python-based finite element library. And then there's Alfvén, which is a C++-based library from Lawrence Livermore, and we'll be using Firedrake. And if anyone's interested, I can tell you how to use Firedrake. It's very simple. Okay, and then to get this structure, these structural properties working, we will be using what's called the compatible finite element method, which in a sense is a close cousin to the mimetic finite difference method, which some people here are using. And on a high level, the idea is, I told you that the evolution equations, your partial differential equations, the solutions live in certain function spaces. Right? And one function space, for instance, is L2, space of integrable functions. Another one is H1, the space of integrable functions where the gradient is defined. But you can also have such spaces for vector fields. So for instance, H curl is the space of integrable vector fields where the curl makes sense, that have enough differentiability for the curl to be applied. And similar, there exists the divergence space where you have vector fields that have enough differentiability for the divergence to make sense. And these spaces we need because we have differential equations that have these differential operators inside. So our fields need to have enough differentiability for these equations to make sense, more or less. And the idea is that then you build finite element spaces that have the same properties. So you want a finite element space for which you can apply the curl. So it has to be fields in a finite element space that may be piecewise polynomial, but still applying the curl makes sense to them. And one property about these spaces turns out to be that these differential operators map from one space to another. So if you take a scalar field in H1 and you apply the gradient, then it will actually give you a vector field that is in the curl conforming space. So you can apply the curl to it, and so on. And we want to build finite element spaces that have this property too. So if you take a continuous Galerkin scalar field on a piecewise linear mesh, for instance, or piecewise biquadratic, and you apply the gradient, then it turns out it will give you a finite element function that is actually in another finite element space, the so-called Nedelec space. And this is how these spaces look like. So for instance, the continuous Galerkin finite element space is the usual space where your degrees of freedom sit on vertices. And you can think of this in a very similar way for finite differences. So this is almost like a finite difference kind of scheme where you have your grid points sitting on these vertices. And the vector finite element space on which the curl is well defined looks like this here, this one. It has directional degrees of freedom because it's a vector field that sit on edges. And the way to think about this is if you have, the Stokes theorem tells you that the curl of a field inside a volume relates to the tangential component of that field on the surface, right? So that's why we want to define our degrees of freedom tangentially along edges, because then it turns out you can define a discrete Stokes theorem. That's why the degrees of freedom are defined this way for my function spaces. Okay. And similar for the divergence theorem that relates the divergence inside a volume to the normal component of your vector field on the surface of that volume. And that's why you want to define degrees of freedom if you find an element space that point in the normal direction of your faces. And this way you can construct finite element function spaces that satisfy this kind of chain where one differential operator maps to another space. And that's called compatible, because the spaces are compatible with each other with respect to these function spaces, differential operators. And the nice thing that you get out of it, after all of this work and all of these funny staggered kind of grids, is you get discrete vector calculus identities. So if you take a function, sigma, that lives in your curl finite element space, then it will identically hold true that the divergence of the curl is 0. And that's what we want, because early on we saw in our zero divergence thing that of the magnetic field that we need this vector calculus identity. And all of this hustle here is just to make sure that this still holds true after discretization. Okay. And so how does this look like for our magnetic field equation, for instance? Well, we can put B to live in this divergence space, so it sits on these faces pointing in the normal direction. We can take our electric field to be in the curl conforming space, so sort of it sits along edges. And then we know in particular that we can apply the curl to it because it sits on edges, so the curl is well defined. And we know that the curl, because of the compatible finite element context, will map this curl conforming electric field into the divergence conforming space, right? If we go to the previous slide, the curl will send the curl conforming space to the divergence space. That's just a fact. So then we know that this B sits in your divergence space on faces, and the curl of E also sits on faces. So this equation naturally holds true and sits on faces, and you can straight up apply the divergence onto this equation. So it works totally the same way as before the discretization. So this is an example of a structure with serving discretization that makes sure that your divergence is always 0, because it very much follows the continuous setup. There's two vector spaces here, one where the curl is well defined and the one where the divergence is well defined. So you can put B in either of these two vector spaces, because B is a vector field, right? So you have some choice. It turns out if you put B in the curl space, it still works out, but it's a little more involved. You have to be a little more finite element theory like about it. You have to take an inner product with a finite element test function, the variational form, and then you have to do integration of the paths and move the curl over to the test function. It's the standard finite element formulation, and that's still divergence-free, it turns out. But I won't go into the details too much. Okay, so that was the divergence, and clearly very heavily relied on the compatible finite element setup where the curl maps from the curl space to the divergence space. How about energy? So recall the idea was that you would compute what is the rate of change in time of your different energies, and then you would match them up and see, oh, for instance, the pressure gradient is equal and opposite to this divergence of the velocity term in the pressure equation. So now you have to make sure you discretize these two terms in a similar fashion so that that still equal and opposite still holds true. So let's look at an example. You can put your velocity into this space that has normal components across faces, the divergence space. In that case, the divergence is well defined. So you can just multiply this by test function and take an inner product, and that will be a valid finite element discretization. Every term in here is fine. But if you, for instance, put the pressure into a discontinuous Galerkin space on cell centers, then the gradient of the pressure does not necessarily make sense, because this discontinuous space that has degrees of freedom only in the cell center is a subspace of L2. It does not necessarily have a notion of what is a gradient. So you need to do something about this gradient of the pressure. And what you can do is you can do integration by parts. You can move the gradient over to your test function. And then you can add some kind of cross-cell flux term. So it feels a lot like the finite volume method. So if you have unknowns that sit inside cells rather than on the boundaries, you have to include some kind of flux that tells you how does the gradient behave across boundaries. So this integral here is a boundary integral, as in a long integral over mesh facets. But now these two terms are not equal and opposite, because here you have something that involves mesh facets, and here you don't up there. So clearly this is not an energy conserving discretization. You will actually have a leak as kinetic and internal energies are transferred. And this is sort of what you would do naively, this kind of discretization here. That's what you would see in the literature if people don't worry about energy conservation. So what can we do instead? Well, we can first move. So we have 1 over n times the gradient of the pressure. We can multiply our density in the velocity equation. And then instead of divergence of test function over n, we would have just divergence of the test function, like this. And that's allowed. Our test function W is in this divergence conforming space with degrees of freedom and facets. And now these two actually look equal and opposite. You have a divergence of something here, divergence of something here, pressure, pressure. So this is perfectly equal and opposite, and this will actually give you an energetically consistent space discretization in your velocity pressure coupling. So that's essentially how it's done in practice. You just have to see these equal and opposite pairs and discretize them in a way that they look equal and opposite. All right, so now we have a discretization that preserves the zero divergence property, and all these energy transfers are balanced. So that sounds like a nice scheme. Let's try it out. This is a 3D test case where you have a magnetic field vortex. It's like a helical magnetic field structure, and you just shift it sideways with some advecting field. And this is how it looks from the top view initially, and that's how it looks like at the end, or how it should look like. But with this energy conserving, zero divergence preserving discretization, this is how it actually looks like. And it's terrible. So what's gone wrong? We did all this effort to conserve all this structure, and yet we get something that's terrible. And the answer is there's something else going on in our equations, which is that we have advection, we have transport terms. And if you're not careful with space discretization for transport terms, then they will produce wiggles at the grid scale. And the reason behind this intuitively is that you can show that if you're not careful with your discretization, then your discrete advection term will actually be advection plus anti-diffusion in a hidden way. So to fix this, you have to add the right amount of diffusion to counter this unphysical anti-diffusion that's hidden in your discretization. And there's a very large amount of literature how to do this, because you want to add exactly the amount of diffusion that counters this spurious anti-diffusion. You don't want to do too much diffusion. That will flatten out your fields. You don't want to do too little diffusion, because then you still get these wiggles. And here it gets even more difficult because you want to add this diffusion without destroying all of your structure, right? You spend all this effort getting a discrete scheme that preserves energy and the zero divergence property. You don't want to add diffusion now that destroys all of that. So how can you do that? And I will give an example of how you do that for the zero divergence condition. So remember, the zero divergence condition of the magnetic field relied on the divergence of the curl being equal to 0. Importantly, it doesn't say anything about what the electric field is. We can use whatever electric field. And so the idea is, let us add a little bit of diffusion inside the electric field, because then we know that we will still have a zero divergence condition after discretization, because the zero divergence condition does not depend on what the electric field looks like, but it depends on this divergence of curl of the electric field. So that's our electric field, right? It's this V cross B term that corresponds to advection, and then some other term that corresponds to resistivity. And it's a finite element formulation, so we have to use a variational form. So we take the dot product with the test function sigma and integrate for every test function sigma in our finite element space. And now we add inside this electric field another term which essentially keeps track of the jumps of your current field J, which is the curl of B, it turns out. It keeps track of the curl of B jumps across facets. And what this essentially says is, if you have big jumps, that's sort of an indication of there must be some wiggling going on. Because I should say, remember, with these kind of vector fields that sit on normal components, that will tell you the normal component has to be continuous, but the tangential component need not be continuous. It's only a partially continuous field. That's why you can have jumps, I should say. So you just say, well, I look at the jumps, and if I do get jumps in my curl of B, I will add diffusion. That's what this term really says. It's a diffusion term that penalizes jumps across your facets. It's called an interior penalty method. And that's fairly common in the finite element method. The key idea here is that you have to hide it away inside the electric field, because then your original magnetic field equation still only sees this curl of E, so it's still divergence-free. Yeah, so that's how you add advection stabilization without destroying the structure. And what we can think of this as physically is it's sort of a resistivity that acts on the grid scale, basically. And that's this term here. So now you will get a loss of magnetic energy corresponding to this grid scale resistivity. Grid scale because it looks at the jumps across facets. And you can also do this in a way that relates to helicity, but I won't talk about that. Okay, so this is how our new electric field looks like. We've only changed the electric field, we've not changed the rest of our magnetic field equation. But we know that this term will take out magnetic energy But we want an energy conserving scheme, so we have to reintroduce this magnetic energy somewhere, right? And now you have a choice. You can either say, I want to take it out, whatever, or you can say, well, actually, my grid scale is pretty close to the scale at which the natural physical resistivity would work. And in this case, you know that the natural physical resistivity turns magnetic energy to heat. So in that case, you would add a term in the pressure equation that would re-inject heat into the system that corresponds to the amount of magnetic energy that you took out in order to stabilize your magnetic field transport. Or alternatively, if you think that actually my physical resistivity is way tinier than my actual grid scale, I should not turn it into heat because that's not what happens in real life. You can instead add a term in the velocity equation that will turn the magnetic energy that you took out into kinetic energy. Yeah.
What all these fudge factors do to the accuracy of the solution?
The interior penalty method will cost you half an order of accuracy. So if it's a second order scheme, you might only be 1.5 order. In practice, it's not as bad. In practice, we get 1.8 instead of 2, something like that. Yeah, that's a good point though. It's in a sense, it's only semi-fudging because if this was the strong solution of your differential equations, you know that the strong solution doesn't have jumps, so this term would disappear because it only looks at jumps. So it's a consistent term in that sense. If you made your resolution infinitely fine, it would vanish. Okay, and if you include this transport stabilization, then your solution looks totally fine. So now we have something that conserves energy and preserves the zero divergence property and also doesn't blow up because of transport. And that's nice. Here's another example where you have straight magnetic field lines, and then you have some kind of circular flow that will start bending your field lines. And it should look like this, right? The field lines get kind of bent. And without this grid scale dissipation, that we just added, this stabilization, your magnetic field lines look like this cyan colored line, so they're messy and all over the place. But if you include stabilization, then they look better. That's good. Yeah, so these are structure preserving methods. They're quite nice because they give you energy conservation and zero divergence property, and it will mess up your transport and you get a bunch of noise, but you can fix that. Long story short. What else can we do with these methods? Because it turns out there's a price for these methods, which has to do with solvers, which I'll skip. But there's some other nice things you can do. And that relates to axis symmetry. In the general run of a tokamak, or a magnetic confinement fusion reactor, your fields are actually axisymmetric in the angular direction. They will always look the same. And 3D simulations are quite expensive, so it's nice to instead use a 2D simulation. And if your field looks the same all the way around the angular coordinate, then you might as well just do a vertical 2D simulation, right? And then when things get more complicated, when you see there might be some instability popping up, then you can switch ideally from 2D to your 3D simulation. So if your simulation takes 10,000 time steps, but only the last 1,000 are 3D, you can run cheaply up to 9,000 and then switch over, right? So here's an example of what's called a vertical displacement event, where your magnetic field lines start moving upwards towards the top, and then all of your hot plasma crashes into the top wall. It's a common macro instability. And one way that people have proposed fixing this instability is using these so-called helical coils that are essentially fully 3D. They're not axisymmetric. They go up on one side and then down on the other. And the idea with these helical coils is that they can break up your magnetic field lines and then your heat will fizzle out all over the wall rather than at this one concentrated point at the top. So it's a way of a controlled stopping of the reactor and equally dissipating heat all over rather than, yeah, it's to avoid getting a large damage up here. And this is an example of how you would first run a 2D axisymmetric code, and then you would turn on this 3D helical coil, but then you have to switch to a 3D code. Okay. So how would you do that? First of all, some notation. This angular direction, I will call the toroidal coordinate, and the RZ coordinates in your cylindrical coordinates, this vertical plane will be called the poloidal plane. And what you can do is you can split your vector fields in a poloidal 2D vector field and a toroidal 1D field that goes around the angular direction. But because it's 1D, you can treat it like a scalar field, right? Because you know what its direction is. So you can ignore the direction and just say, well, it's a scalar field on your vertical plane. So you take your R phi C components of your vector fields, and you keep a 2D poloidal part and a 1D out of plane scalar part. And making things axisymmetric does not mean that you throw out the out of plane part. It just means that you make all the fields independent of the phi coordinate. So some people call this 2.5D because you still keep the out of plane component. But in reality, it's only 2D because you only have two coordinates, R and C, because you skip the phi one. And then you have to use, instead of the curl, the 3D curl, and the divergence, you have to use these 2D planar operators, rad and rad perp. And then you can split all of your equations into a poloidal part, that's a vector equation, 2D vector equation, and a toroidal part, which is a 1D out of plane equation, so it's a scalar equation. This B toroidal is a scalar field that lives in the 2D poloidal plane. And the good news is, after you do the split, you can still do all of this compatible finite element stuff. You can have 2D spaces that map onto another using your 2D differential operators. And all the equations still work out, and you still have energy conservation, zero divergence property, and so on. But I won't go into the details here. What I do want to say, and here's an example of a vertical displacement event where sort of all your temperature and your energy gets sucked up to the top. But the good news is, which is what I was going to get to, is it turns out three-dimensional compatible finite element spaces can be built by gluing together a 2D compatible finite element space and a 1D compatible finite element space chain. And that's nice because you can then first run the 2D simulation and then seamlessly at some point load the 2D data into your 3D finite element fields, and you will not lose any information. Normally people have to project across spaces and they will lose or take averages to load from 2D to 3D. So here's an example of a 2D divergence space that has degrees of freedom in the normal direction across facets, like you need for a divergence space. And then you take a tensor product with a one-dimensional space to get this 3D space. And you can do the same thing on the other side. You take your 1D out-of-plane scalar space, take a tensor product with an out-of-plane angular direction finite element space, and then you can glue these together to get your three-dimensional divergence conforming finite element. And there's no averaging or anything involved. That's quite nice. Yeah, I'll skip the solver stuff because it's already getting a little late. But just as a quick flavor, essentially, solving something efficiently relates to timescales. And if you have a very fast timescale that's much faster than you worry about, then you want to use implicit in time discretizations to step over these fast timescales. And in magnetic confinement fusion, in tokamaks, the fastest timescale are magnetic waves, which are much faster than the kind of instabilities that we're interested in. So you have to use implicit time discretizations. But you have these very funky, kind of looking, confusing derivatives like a curl of a B cross and a curl of a B cross, and they lead to very difficult to solve operators. And that's essentially the gist of this. Is very much still an open research problem, how to solve these efficiently. Yeah, and that's essentially it. Thank you.
Are there any questions for our speaker?
What computers do you solve these simulations on, and how long do they take?
So we have internal clusters in the Alamos that we use, and then we also use the NERSC machines. One of them is Perlmutter. As to how long they take, standard kind of magnetohydrodynamic codes for tokamaks take days to simulate 0.1 seconds, for instance. So it's very quite slow. But 0.1 seconds is essentially how long this instability take. So it's kind of long enough to figure out these instabilities. In terms of this actual code, I only very recently figured out how to solve it efficiently. So I don't actually have results at scale quite yet. But yeah, days on, yeah.
I suppose the next question is, because I don't monitor tokamaks and things like that. I'm assuming you don't have a tokamak at Los Alamos.
No.
Okay. And you're just doing raw science and simulations and computational science. And you just said that it only takes 1 second for the confinement to crash and burn. Is that what you just said?
Yes.
Okay. So do you just get on a plane every now and then and say, well, we think, okay, have you actually, do you tell the tokamak people, whatever, tweak the magnetic field in a certain way or something like that, and see if it doesn't crash and burn the tokamak, and it lasts until 2 seconds or something like that?
There's 3 answers to that. The first answer is existing research tokamaks are quite more robust than the commercial ones we want to build. So on existing research ones, it doesn't matter so much if it actually does produce a crash. In practice, it will give you a big kind of scratch in your wall, and you can just replace the tiles. And on research tokamaks, you can do that, but on an economically viable one, you can't, because you'd have to stop operation for some time. So you can actually do simulations where things crash in real life. First answer. Second one is, as of this moment, it's even unclear what is the ideal design for a tokamak. So with these simulations, you can figure out a priori what should be a good design that leads to fewer instabilities, right? So you can do tokamak design with these simulations. And the third answer is, in practice, it is true that you have to do real-time control with your plasma in order to avoid these instabilities. And this has to be very fast. So what people are thinking of doing is to use machine learning and machine learned control, because machine learned programs are quite fast. They're fast enough to actually react in time to control your plasma. But you need to learn these programs in something, right? So people try and produce data from standard discretization methods that you can then use to learn a machine learning method, which you can then use to react adequately in time. That's the
They have one? A machine learning method?
Do we have one?
Well, do you have one or somebody else has one? Or-
Yes, so this is something that people in particular at the University of Lausanne in Switzerland are working on a lot, and they have some promising methods there. Yeah.
By the way, we have, this is information for whoever is interested. We are involved with the partnership with General Atomics, and we can get data for people who are doing machine learning here in the university to do studies using real data from the real tool.
How many elements do you need in 2D and in 3D to do a worthwhile simulation?
It's a good question. In 3D, we usually run with around 10 million degrees of freedom, something along those lines. So not tiny, but also not very big. Right.
What did you just say? How many degrees of freedom?
Around 10 million.
Okay.
That's the 3D case.
That's the 3D case.
And so when you're just doing a slice,
The slice would be 100K, 200K, maybe. Let me think. 200K, yeah. So the 2D slice we usually do with direct solvers for that reason, because it's more than enough.
Do you look at just tokamaks or do you look at like accelerators and other?
We have in the past only looked at tokamaks, but it is totally on one of our plans to also look at accelerators. The reason why is because you can actually construct finite element meshes for accelerators quite efficiently by starting with a 2D vertical plane. And then you do an extrusion, and this is an example of an extruded finite element, and the extrusion sort of rotates as you extrude. And that way you can efficiently make a finite element mesh that has an extrusion. And so, yeah, we'll be looking at that too. That's a good question.
So for your calculation, do you take parameters from machines that use
For what?
for those machines, tokamak, for example? Is it general or is it tied to the specific?
Oh, this one, for instance, is the eta geometry, or slightly simplified eta geometry. So we do use real geometries.
Oh.
In practice, it will get more complicated because some of the, for instance, accelerators have certain pieces sticking out that are a little harder to mesh. But yeah.
So do you also include interaction collisions?
That's a very good question. So early on, I said you can have microscopic effects and macroscopic effects. And microscopic effects, you would use particle simulators. So you would push a finite amount of particles around. And ideally, you want to couple these two types of simulations. That's called hybrid simulations. And we have a team that works on the particle part. We have yet to couple it, but there do exist hybrid codes out there. And it's an important part of studying certain instabilities.
I have a very quick question on I know you just very quickly showed the solver slide. You said you have some fast timescales, and for that you're using implicit.
Yes, it's the one in the red boxes. That's the fast timescale. And
so do you use like a sort of like IMEX scheme, like implicit explicit? Do you split the terms in the PD and treat them?
Yeah, that's a good point. In practice, we use an implicit split discretizations, and rather than IMEX, we use IMIME. And we put the orange parts on one side. And the hard parts really in this problem are the red boxes and the heat flux. And if you split out the orange boxes, then the red and the purple are decoupled, and you can solve them separately. And then we have specialized solvers for the heat flux on the one hand, and this Alfvén wave, magnetic wave coupling on the other hand. And they're very small. We usually just put them together with the Alfvén waves because it's a similar type of term. This is a curl, B cross curl, and that's a curl, but a similar nature.
And so you just said very recently you have discovered how to implement this efficiently.
Yeah.
I don't have data yet, but what did you mean by did you use fire drake for the efficiency?
No, the efficiency comes more standard algebraic multigrid methods don't work for this B cross B cross curl curl. So standard algebraic multigrid methods are designed for isotropic problems like a curl curl or a div grad. But as soon as you have some directional effects, which you get in this case from B cross, then standard multigrid methods have a really hard time. And so me saying that we figured out how to solve it efficiently was more me saying, how do we trick this kind of system into looking like something that can be solved by standard methods? So it's more a math kind of thing.
Okay.
That's a good question.
If there are no other questions, then let's thank the speaker.
I got one last question.
Sure.
Yeah, on the tokamak geometry,
Uh-huh.
3D, you know, the actual construction.
Uh-huh.
Is it have to have that type of shape, or can you shape it like Santa Claus, because this is Christmas season? And does something like that even kind of make sense if you get?
There's one fundamental truth, which is that because you have to wind your magnetic field lines around, it always has to be some type of torus. But then how exactly the torus is shaped is up to you. You can do a stellarator where the torus wiggles around. You can have more kind of, they're called spheromax. The torus is to look almost more like a sphere. So there's some freedom
So
there.
you
It's
can't
not
have,
symmetric,
but you
right?
can, I suppose you could have a Santa Taurus.
Yeah, you could. Yeah.
Okay. Thank you very much.
Thank
Give me
you.
applause.
Yeah.
My question was, it's not symmetric, right? It looks more like an earlobe, like the top part is a little different from the bottom.
Yeah, the vertical cross section is not symmetric. Yeah. Only the phi. Yeah. That is
Okay.
true.
Well, thanks again for the great talk.
Thank you. So thanks for coming.